So again, we're talking about concurrency, and where we left off, we were just about to start into this slide here to discuss why we might care about writing multi-threaded applications in the first place. So I just have a few examples of situations or reasons why we might want to do this. Probably the most important one is the first one that's given here, which is that most systems these days use multi-core processors. So if you choose to write your application as just a single-threaded application, you can't really fully utilize the computational power that's available to you, because if you have a single thread and you say you have like a 4-core processor and your application is written as a single thread, then that thread will run on one of the cores, but then 3 of the other cores are sitting idle. They have nothing to do, at least with respect to your program. So if you want to fully utilize the processing capability that you have available to you and you're using a multi-core processor, you're forced to write your application as a multi-threaded application. Otherwise, you'll never be able to fully utilize all the processing power that's available to you. Another reason that we might go with multi-threading is in order to keep the process responsive. So just as an example, maybe you have a graphical user interface, some graphics application with a graphical user interface, and you have some operations that the program needs to perform that are quite slow. So you don't typically want to have like really big lags in the response between user inputs to the graphical user interface, like maybe a mouse click or something like that, or they type something on the keyboard and then they have to wait for 30 seconds for something to happen in response to that. So a good sort of strategy for addressing this sort of issue in a graphics application is you have one thread for sort of dealing with the UI, so like basically processing the events, mouse click and so on. And if there's something that the user does through the user interface which initiates something that's going to require a lot of computation time, what would happen is that the user interface thread would just signal to another thread that, hey, there's some computation that needs to be done. And then immediately the user interface thread would go back to dealing with the user interface, like basically waiting for other events like mouse clicks and so on. And then this other thread would start up and do the actual processing. And in this way, you get a very responsive user interface, because the thread that's handling the user interface never does anything that's compute intensive. It's just basically in a loop waiting for an event to happen, like a mouse click. Then it does something to initiate other processing based on that, which is done in another thread, at least if it's time consuming. And you could have a similar sort of situation in a completely different application area, like maybe a network server, where you have maybe one thread which is sitting listening for incoming network connections. But once it gets an incoming connection, it then spawns off another thread to actually process the particular connection that's been established in order to be responsive to other incoming connections. Another reason that you might want to use multi-threading is for some types of structures for a program, it might make sense to use threading in the sense that it can simplify the code, because it just naturally, like for example, suppose you have an application where it naturally needs to perform a number of different tasks, and those tasks have to be scheduled in some way. So if you wrote things in terms of a single-threaded application, then you'd have to effectively do something similar to like context switching and stuff that the operating system does, but you have to kind of simulate it yourself to switch between different tasks. But if you write your application instead as having multiple threads, then you can let the operating system basically worry about the scheduling, because it will schedule the threads for you. So for certain types of applications that have a structure where you maybe have a bunch of tasks that you want scheduled, it might make a lot of sense in those situations to use a multi-threaded application, and perhaps it might actually simplify the code somewhat as well. Anyway, so this just gives some examples of why you might want to have multi-threaded applications, but probably arguably the first one is maybe the most important. The next thing I need to talk about are memory models. So memory models are, well, in general, they're important, but when you start talking about concurrent programming, then they start to be kind of even more important. Memory model is sometimes referred to as a memory consistency model. And essentially what it is, it's essentially an interface description of the interface that's presented by memory to the programmer. So you can think of it like a contract that the memory promises to behave in certain ways when you do certain types of memory accesses and so on. And in order for a program to really make any sense, to have like a well-defined meaning, you need to have some kind of well-defined memory model for the program to be running with respect to. And memory models typically need to address issues, well, there's really two. One is ordering and one is atomicity. So essentially what's kind of embodied by ordering is if you have multiple threads and they're all accessing memory, there's the issue of like, what order do different threads see changes to memory being made into, or made in, I should say. And when do things become visible? When do changes to memory become visible? One thread changes a particular variable. When does this become visible? This change to another thread, which might be running on another core. Then atomicity is dealing with whether the memory operations are atomic. So atomic just means that, you know, when an operation, from the time an operation starts till the time it ends, there can't be any other intervening things happening. So when we talk about atomic memory operations, for example, if I'm doing a read from memory and it's atomic, once I start reading from that memory location, I'm guaranteed that no other thread can come in the intervening period and either read or write that memory location. So it means that once a memory operation starts, it goes through to completion before anyone else can access that location. And the particular memory model that's used, it has kind of three important consequences. One of them is the ease of programming, in other words, the programmability of the system. Generally speaking, the stronger the guarantees that are made by the memory model, like the more constraints that it places on itself, the easier it is to write code with respect to that memory model, at least to write correct code that works properly. The downside is the more constraints that the memory model places on itself, in other words, the stronger guarantees it makes to you about how it behaves, the performance is likely to degrade, because the more constraints it places on itself, there's less optimizations that it can perform and so on. Therefore, the performance is likely to be much worse. It can also affect potentially the portability of code too. So if you write your code with the assumption that a particular memory model is the one that you're using, and then you want to port your code over to an architecture that can't handle that particular memory model, maybe because the guarantees are so strong that it actually can't implement some of them, then you're stuck with a situation where you have to maybe rewrite a lot of your code in order to be able to port it over to another architecture. So code portability also can be an issue with respect to the memory model. Any questions so far? So another thing that's really important with respect to concurrent programming is what's known as sequential consistency. So there's a formal definition that's given at the top of this slide, which is rather long, but the basic idea is if you have a runtime environment which is sequentially consistent, like this is referring to the environment in which a particular program is running, essentially what sequential consistency guarantees, if you have a multi-threaded program, the program will run as if the instructions from the different threads are interleaved with one another. And this is probably best illustrated by way of an example. So what I have on this slide is a very simple program that consists of two threads. And the first thread essentially we have variables x, y, a, and b, and they're all integer values, and they're all initialized to 0 as well, just to make the example simpler. So the first thread, all it does is it initializes one of these variables x equal to 1, and then assigns y to a. And then thread 2, it sets y to 1 and assigns x to b. If this code is run in an environment which is sequentially consistent, this places some constraints on the order in which things can happen. And essentially what it does, it allows for a kind of arbitrary interleaving of the code from the two threads, subject to the constraint that you can't reorder any of the instructions from a single thread. So for example, one particular sequentially consistent execution of this program would be, we first execute the first instruction in thread 1. So basically this instruction here. Then we execute the first instruction from thread 2, which is what this corresponds to. Then we would execute, for example, the second instruction from thread 2, which is this one here. And then we execute the last instruction from thread 1. And the important thing to notice, if you read through the order here from left to right, notice that the instructions from thread 1 run in the order that they appear in the source code. They run in program order. So this is the first instruction from thread 1, and then the second instruction. You can't invert the order of the code within a single thread. This kind of makes sense. It would probably be quite a disaster if this were to happen. So this is essentially the guarantee that sequential consistency makes. And there's quite a few different possible sequentially consistent executions of this program. We could also, for example, have this sequentially consistent execution here, where we first run the first instruction of thread 2, then we run the first instruction of thread 1, then we execute the second instruction of thread 1, and then the second instruction of thread 2. That corresponds to this ordering here. And there's a number of other ones as well. But there's certain things that we can't do. Like we couldn't have a sequentially consistent execution where this line here, the second line of thread 1, executed before the first line. This would violate that. Any questions about what this means? If you've taken a course in concurrency before, which I imagine a lot of you have, at least if the ones from computer science, you're probably familiar with this terminology already. But again, I want to make sure that everyone has a similar sort of background. So the sequential consistency memory model, or the sequential consistency, implies a particular memory model. There's a memory model associated with it. And essentially this memory model implies that all memory operations are atomic. This is because essentially sequential consistency serializes the instruction stream. You're basically choosing one instruction from one thread to run, then another instruction from another thread, and another instruction from another thread, but only one thing effectively is really running at one time. So you can't really have the possibility of having two memory accesses happen at the same time, because you're essentially serializing the execution of the code. So all memory operations are essentially atomic, and all writes to memory become visible simultaneously to all threads. And this might seem like a trivial thing, but it's not at all. It's a very non-trivial thing that all writes become visible to all threads at the same time. Unfortunately, sequential consistency, this particular memory model, it precludes almost every useful optimization that we want to do, either in hardware or in terms of optimization that we might want to perform by a compiler. So depending on what your background is, some of these terms may or may not make sense to you. But for example, things that are optimizations that are done in hardware, things like store buffers, well, caches we've talked about, obviously, out of order instruction execution. Whether you're aware of it or not, when you compile your code, you get a certain CPU instructions for your code. When you actually go to run it, the processor can just say, well, I don't really like the order those instructions are in, and it can reorder them and execute them out of order on the fly, as long as it doesn't violate data dependencies between the data, the various different operations that are happening. So there's a lot of hardware optimizations that can be performed, and also effectively, many of these operations sort of, the similar effect can be achieved by doing certain sorts of transformations on your code in terms of optimization in the compiler. A very common optimization in the compiler is to reorder loads and stores. Loads and stores are just reads and writes to memory. So often reads and writes can get reordered just because it can maybe help to hide some latency with memory accesses and so on. These sorts of optimizations are also effectively precluded by sequential consistency. So although sequential consistency is sort of very intuitive, like the idea that the code for the different threads just interleave is kind of a very natural thing. It's kind of, relatively speaking, easy for us to understand and wrap our mind around how our code's actually going to behave when we run it. It's still complicated because there's a lot of way the code can interleave, at least for like a more complicated program, but at least it's kind of manageable in terms of the complexity to understand. But the downside of sequential consistency is that you pay a huge price in terms of performance, because it's it makes such strong guarantees that the hardware basically is precluded from doing almost any useful optimizations that it would want to do, like no caches, no out of order instruction execution, no reordering of loads and stores, either by the processor or by the optimizer, and so on. So what I want to give here is just an example to illustrate like reordering of loads and stores, and to try to kind of explain or give you some insight into why it is that this can be problematic. So essentially what we're talking about here is a compiler optimization that can be applied to your code, that if the compiler were to do it, it effectively destroys the sequential consistency of the execution environment in which you're running your program. So I just want to make one comment before I go into this example, which is that although I have like C++ like syntax in these examples are not C++, because C++ does not use sequential consistency for its memory model. Therefore, anything that we talk about here is kind of meaningless in the context of C++. But just because we're all familiar with the syntax of C++, for the code examples, I'm using C++ syntax. But it's important to understand this is not really C++ code, because there is no sequential consistency kind of guarantee for the code that would be running here. Anyway, so what I'm considering in this particular case, just a very simple single-threaded application where we have variables x and y, and they're initialized to 0. And then essentially we have two lines of code here which are initializing each of these variables to 1. They were initially 0 and we're setting them to 1. And then there's some other code here which is not really so important what it's doing from the point of view of the example, but the dot is just some other code, presumably which is using the values of x and y to do some kind of computation. And what I want to consider here is, suppose the compiler, when we're compiling our code, it says, well, because of what we're doing in the dot here, it would be better if I first assign to y and then assign to x. In other words, it would be better if I reverse the order of these two stores to memory. So it basically rewrites our code like what's shown in the optimized version of the code down below here. And of course, it's obvious, even without knowing what the dot is, it's obvious that these two pieces of code are going to behave in the same way, because there's no dependencies between these two lines of code. Like this line of code involving y doesn't use x, and this line of code using x doesn't use y. So if I switch their order, it can't have any change. It won't change the overall behavior of the code. So this is a valid thing to do. In other words, the optimized code will run as if it was the original code. It has the same observable behavior. And generally speaking, compilers are at least in the C++ world, are free to do pretty much anything they want to optimize your code, as long as your optimized code runs as if it was the original code. In other words, it has the same observable behavior. So in the context of a single-threaded program, so what we're looking at here is a single-threaded program, this is a perfectly safe optimization to do. The compiler can reverse the order of these two stores, and the program will behave in exactly the same way as before. But what I want to do next is I want to consider what happens if we bring a second thread into the picture, and then the compiler makes a similar sort of optimization, and then we watch things break. So in this particular case, I'm going to have an application with two threads. So the code for the first thread is identical to what we had in the previous example. So all we're doing is essentially adding a second thread of execution. And what this thread is going to do is it's going to, well, basically do what we have here. It's going to test if the value of the variable y is 1. And if it's 1, then it will assert that x must be equal to 1. And I guess the comment that I want to make with respect to this code here is if we kind of look at this code and imagine that we're running this unoptimized code, it's never the case that this assertion can fail. If we kind of think about, assuming again that the program is running on a sequentially consistent machine, so basically the only way we can execute the code from the threads is by interleaving them. So there's various different combinations of how we can interleave things, but for example, maybe we execute both of these lines from thread 1 first, in which case both x and 1 are set to, x and y is set to 1. And then we start to execute the if, then we check if y is 1. Well, it's 1 because we just set it to 1 a little bit ago in thread 1. Because it's 1, we go into the assertion, then we assert that x is 1. Well, x is 1 because we already set it to 1. And any way that we come into this assertion here, the only way we can come into this assertion here is before we hit the if, this thread is set y to 1. Otherwise, the assertion can never be executed. So the only way it could fail is that we set y to 1, and yet x is not equal to 1, or x is x is not equal to 1. But no matter how we try to reason about this, if we're executing this code in a sequentially consistent manner, if y is set equal to 1, then x always must be set equal to 1, because the only thing that ever sets y to 1 is this thread. But in order to get to this line here, if the machine is sequentially consistent, this first line must have executed, which means x must be 1. So there's no way in which this assertion can ever fail. So like if we're running this on a sequentially consistent machine, we know for sure that an observable behavior of this program cannot possibly be that the assertion fails. Does that make sense so far? Okay. Now what we're going to do is we're going to say, suppose now that the compiler optimizes the code. And in particular, it's only going to do one very innocent looking thing. It's going to do the same optimization that it did to our single-threaded application on the previous slide. What it's going to do is it's going to interchange the order of these two stores to memory. So instead of doing x and then y, it's going to do y and then x. And we just saw before that if the environment that's being provided that this program is running in is sequentially consistent, this program cannot possibly fail the assertion. But if we then allow the compiler to make this optimization here, what happens is now the assertion can fail. The observable behavior of the program will change. The reason why is, for example, again, assuming that the machine is sequentially consistent, we could have an execution that goes as follows. We set y to 1. And again, remember the variables are initially 0, so x and y are initially 0. So we set y to 1. And then before any further execution happens in thread 1, we then test the if over here. Well, y is 1 because it just was set to 1. We go into the assertion and we assert x is 1. Well, it's not 1 because we haven't yet reached this line in the other thread which sets it to 1. So it's actually 0, the initial value that it had, and the assertion fails and the program crashes. So effectively what I'm trying to show here is that even though we have a sequentially consistent environment in which we're running the program, the fact that the compiler applied a very innocent-looking transformation, a very innocent-looking optimization to our code, causes the overall combination of the environment we're running in, which is sequentially consistent, plus the mangling of our code that the compiler has done, the optimization. The combination of these two things destroys sequential consistency. Overall, what we end up with is something that doesn't run as if it was running in a sequentially consistent environment. Because of the optimization the compiler performed. And this is like a very trivial program, like it's just a few lines long. So you can imagine like there's no hope for any kind of practical world program working if the compiler starts reordering loads and stores. Because even in this very trivial example, things break. So again, this is just to illustrate by way of a software optimization how we can break sequential consistency. So basically, if we want to maintain sequential consistency, the compiler can't do this type of optimization. And pretty much any kind of hardware and software optimizations we might want to do, we can't do. So the cost of maintaining sequential consistency becomes very high potentially. Any questions about this example before I go on? Okay, there's a corresponding example for like a store buffer, which is kind of a similar sort of problem, but with hardware optimizations being performed, and then they cause problems with respect to sequential consistency. The next thing I want to talk about is atomicity of memory operations. So sort of baked into sequential consistency is the fact that memory operations are atomic, or at least they appear as if they're atomic. For our purposes, essentially they're atomic. And the downside of this is that atomic memory operations require synchronization. Because again, what an atomic memory operation is, it's a memory operation that's guaranteed to go from start to finish without any other intervening accesses to that memory location. So if you imagine that each of us is a core in a multi-core system, and we're each running a thread, if I want to do an atomic memory access, it's not by magic that somehow while I'm accessing that location, none of you access it. I mean, what happens is that before I go to access it, I have to say, hey, everyone, please, for the next little while, do not access this memory location because I'm about to access it and I want to do an atomic access. So I have to communicate to you and say, like, don't access this location. And I have to wait a little bit of time to make sure there's sufficient time for you to receive that announcement that I'm making. Then I proceed to change the location. And then when I'm done, I have to say, okay, everyone, I'm done. Now you can actually go and modify that or change that location or read its value if you like. But all of this takes time because the synchronization doesn't happen by magic. Like the processors actually have to communicate with one another and signal their intent to do an atomic memory access and so on. So because of this, we really don't like atomic memory accesses because each atomic memory access requires all this interaction or synchronization between the processors. So really what we'd like is nothing being atomic. So there's also this downside to sequential consistency, which we don't like the atomicity that goes along with it because it adds additional overhead. So let's suppose that we actually do away with atomicity. So we have something that's a little bit like sequential consistency in that the instructions sort of interleave, but not quite interleaving. You can also have instructions from two threads running simultaneously. So it's not quite interleaving, but something a little bit similar in the sense that we still execute all the instructions from each thread in order, but we can have threads each thread can be doing instructions at the same time. So we actually have parallel execution potentially of code. If we do something like this, then we open up another sort of problem, which is what's referred to as data races. So as soon as we have not all of the memory operations being atomic, we can have something called a data race. So what exactly is this? Before I can introduce the notion of a data race, I first need to introduce the notion of a conflicting memory access. So if we have two memory operations, we say that they conflict if they're accessing the same location and at least one of them is writing to that location. This is critical. Someone has to be modifying the underlying data. So a data race is simply a conflict. If you have a conflicting memory operation, it forms a data race if you have different threads that are performing the memory operations, and it can happen potentially at the same time. So this is maybe best illustrated in terms of a code example down below here. So here what we have is a multi-threaded program consisting of two threads. We have the variables x, y, and z. They're integer variables, and they're all initially 0 before the program starts up. If you look at what's happening in this code in these two threads, we have data races on both the x and y variable. There's a data race on the x variable because here we have essentially a write to the variable x. So the chunk of memory that holds x is going to be written to here. In this thread over here, we're reading x. So this would correspond to conflicting memory operation because here we're writing and here we're reading the same variable. So this is a conflict. But what makes it a data race is that these things can happen at the same time because you could have the execution follow the following timing where thread 1, while it's trying to execute this, thread 2 has already executed the first line. It's proceeded on to the point where it's about to read x. Then thread 1 starts up and it writes to x. So thread 1 is writing to x at the exact same instance that thread 2 is reading x. So because they're both accessing the same location, at least one of them is writing, and they're happening at the same time. This is a data race. And a similar thing can also happen for the y variable, because we could have the execution follow the following pattern. Initially, thread 1 starts up, it executes the first line, then it proceeds on to the second line, it's about to read y, then thread 2 starts up and it's writing to y. So you have the situation where thread 2 is writing to y, at the same time that thread 1 is trying to read y. Again, we have a conflicting access because they're both accessing the same location, the location that holds the value of y. At least one of them is writing, and they're happening at the same time. So this is a data race. In contrast, though, the variable z doesn't participate in any data races in this program. You might say, well, wait a minute. I mean, we could hit the situation where thread 1 hits this line at the exact same time thread 2 hits this line, and this one is reading z at the same time that this one reads z. But this is not a data race because there's no conflict, because an essential part of a conflicting memory access is at least one of the threads has to be writing. But in this case, they're both reading. You can have a million different threads all reading the same variable at the same time. There's no data race. There has to be some kind of modification involved to have a data race. So any questions about any of this? I mean, essentially, if you have data races, the thing we don't like about data races is they can lead to very unpredictable behavior in your code. And we'll kind of go through this in a little bit more detail and look at how this can manifest itself. So what are some of the things that can happen as a result of data races? Well, data races can result into things called torn reads and torn writes. So a torn read is just a read operation that, due to the fact that the memory access is not atomic, that the read starts up, it starts to read memory, but before it has a chance to finish, another thread comes along and it does a write operation to the same address you're reading. So you essentially have like a read and write that are overlapping. This is what we call a torn read. And just to illustrate sort of the consequences, or at least some of the consequences that can result from a torn read, I want to consider a specific example. So suppose we have an architecture where integers are 2 bytes, so like basically 16-bit integers, and they're big endian just meaning the more significant bits are stored first and like at the earlier address. And I'm going to use hexadecimal just because it's a little bit more convenient to break things into bytes if you use hexadecimal. So the first 2 digits in hex correspond to 1 byte, and the second 2 digits correspond to another byte. So the first byte of this storage for this value that we're initializing x2 would be 1, 2, and the second byte would be 3, 4. And what I want to consider is a situation where we have 2 threads, and thread 1 is going to read x, and thread 2 is going to write the specific value 5, 6, 7, 8 in hexadecimal to the variable x. And these are going to happen in an overlapped manner. So the time when these are happening are overlapped in time. And I'm going to consider a very particular timing just to illustrate, one way in which things can go wrong. So suppose that an x is initially 1, 2, 3, 4, like stated up above here. So because we're storing the integers in big endian order, the most significant byte comes first, the one with the more significant bits. So 1, 2 is in the first byte, and then 3, 4 is in the second byte. And suppose now that thread 1 comes along first and it starts to initiate its read of memory. So it's going to try to read the value of x. So it starts to read the value, so it reads the first byte, which is 12. But suppose now before it has a chance to finish, it hasn't yet read the second byte. Before that happens, thread 2 comes along, it writes 5, 6, 7, 8 to that variable x. So what's going to happen is 5, 6 is going to get written to the first byte, and 7, 8 gets written to the second byte. And now after that's finished, now finally thread 1 gets to finish its read to memory. So it reads what's in the second byte, which is going to now be the value 7, 8, because thread 2 just wrote the value 7, 8 into it. So it reads 7, 8 out of the second byte. So if we combine together the results that thread 1 read, for the first byte it read 1, 2 in hex. For the second byte it read 7, 8. So overall the value that it read for x was 1, 2, 7, 8 in hex. But notice that 1, 2, 7, 8 is not the value that the x originally had, which was 1, 2, 3, 4. It's also not the final value that it had, which was written by the other thread, which is 5, 6, 7, 8. It looks kind of like a random value. I mean, effectively what you have is you have part of the old value, part of the new value combined together. And this is the value that actually got read by thread 1. And this is a really horrible kind of behavior, because the value that is read is never a value that was actually written to this variable. So it's almost as if you're just pulling random values out of the air. I mean, they're not truly random, but in terms of the behavior you observe in your program when you're trying to debug it and figure out what's going on, it's kind of like your program just starts reading random values out of your variables, which obviously is going to cause all kinds of horrible things to try to debug. And then we can have a similar thing with writes to memory. We can have what's called a torn write, which is just kind of an analogous sort of definition. So this is a write operation that, due to the fact that memory operations are not atomic, that while you're writing, another thread can come in and either do a read or write to the same location that you're trying to write to. So just to give an example to illustrate how this can go wrong, again, suppose you have an architecture with 2-byte integers and it stores them in big endian order. And we have this variable x, and it's initialized to 0. And then what we're going to consider is a situation where thread 1 wants to write the value 1, 2, 3, 4 to this variable, and thread 2 wants to write 5, 6, 7, 8. Again, these numbers are in hexadecimal just to simplify the example. And then, so initially we have x is 0 because this is how things are defined. The value is initially 0, so we have 0, 0 in both bytes. And then suppose we have the following timing. Thread 1 comes along and it writes 1, 2, well, it's trying to write 1, 2, 3, 4 into the variable. But suppose it only has time to write the first byte, and then thread 2 comes along. So it writes the first byte 1, 2 into the most significant byte, but the other byte's still unchanged because it hasn't had a chance to write to it. And then suppose thread 2 comes along before thread 1 finishes this write to memory, and then it writes 5, 6, 7, 8 into this variable. So it writes 5, 6 into the first byte, 7, 8 into the second byte, and then once it's finished, now thread 1 is able to continue along, and it writes the remaining byte, 3, 4, into the least significant byte of this value. So it writes this one of 3, 4. The overall effect that's achieved here is the value that's written into X is 5, 6, 3, 4. In other words, this value here. But notice that 5, 6, 3, 4 is neither of the values that were written to that memory location. The only things that any thread tried to write to that location was 1, 2, 3, 4, and 5, 6, 7, 8. But the value that we end up with in that location is neither one of these values. Again, this is kind of bad news. Effectively, what we have is almost as if just spontaneously random values appear in memory that we never wrote there. I mean, this is not really what's happening. Essentially, what's happening is we're writing part of 2 different values into the memory location, and we end up with something that was neither value that we wrote. And again, if you can imagine, this can cause all sorts of weird bugs and things to happen in your code if this arises. Okay, so just kind of put together some of the ideas that I've been introducing so far. So essentially, we have this thing called sequential consistency, and then sort of the memory model that it implies. And on the positive side, it's very easy, relatively speaking, to reason about code that follows this particular memory model, because it's relatively simple to understand what the possible outcomes are in terms of how your code can run. So we like it from that point of view. It's easy to program for a sequentially consistent machine. But the downside that we've seen is that all the performance goes down the drain, because all of the optimizations, or at least most of the optimizations that we'd like to do, either in hardware or in software by an optimizing compiler, these things are all precluded if we want to have a machine which is truly sequentially consistent. So how can we try to rectify this? Because we don't really want to have really poor performance, but we also don't want to have things be like really impossible to write code for either, because it's very difficult to reason about what the code is doing, because the memory model is so weak. It makes so few guarantees that you can't really tell what your code's ever going to do anymore. So the compromise that a lot of languages have kind of eventually over time converged on, and essentially what's done in C++, is it uses a memory model called sequential consistency for data race-free programs. So essentially what it does is it says, well, first of all, we don't want to make all memory operations atomic, because this requires synchronization, and this is going to slow things down. So atomicity goes out the window. We can request it if we want it, but by default, things are not going to be atomic. So atomicity goes out the window. Because of this, we can have data races. So what this particular memory model says is that you don't write data races in your program, and I guarantee that you can't tell the difference between running your program on this runtime environment versus one that's truly sequentially consistent. And this is not the same thing as sequential consistency. Essentially what you have, you can think of the space of all possible programs you could ever write. There's infinitely many. So you have the space of a set of an infinite number of programs. And essentially what we do here is we say, any program that you could run in this space of programs that you could tell that you're not running on a sequentially consistent machine, I forbid you from running those programs. You can't write that code. Don't do that. And effectively, this is what we're doing here. We're saying, because it turns out that the kind of optimizations we're going to allow here are ones that the only way you could detect the fact that the underlying hardware and the optimizer are doing really sleazy things, completely reordering your instructions, doing like loads and stores all out of order, caching things all over the place. The only way that you could detect the effects of these things is you inject a data race into your program. And it turns out that by doing things in this way, this allows a lot of latitude for optimization. So all the things that we want to do, pretty much, we can do. But the benefit that we get is that still, as long as you don't have data races in your program, it's easy to reason about your code. It's going to behave as if it was run on a sequentially consistent machine, which makes it, relatively speaking, easier to reason about than if it wasn't, because sequential consistency is a quite strong memory model, a quite strong guarantee made by the system. Anyway, so this particular model is known by the acronym SC-DRF. And essentially C++, C, and I believe Java as well use this particular memory model. Any questions? And I guess I've already covered part of this slide. So again, C++ uses sort of as the default memory model sequential consistency for data race-free programs. So because of this, in C++, when you're writing code, thou shalt not write data races in your code. If you do this, it's undefined behavior, because as soon as the machine is not behaving in a sequentially consistent manner, like you really don't know what your code's going to do. So if you do anything, it injects a data race, because this memory model says as long as there's no data races, you can reason about your code as if it's being run by a sequentially consistent machine. But if you inject a data race into your code, typically you don't do it deliberately, it's by accident, you have a bug in your code. As soon as that happens, all of the reasoning that you have about like these are the possible outcomes of the code, all of this goes away, because the reasoning was based on the assumption that the code is running as if it was being run by a sequentially consistent machine. So it's really, really critical in C++ that you not have data races in your code. And of course, one of the very common bugs when you're writing concurrent code is you have data races. It's like one of the most common types of bugs.
So is it a compile error or runtime error?
Oh no, no compiler. Your code's just hosed, and these are often very difficult to detect too, because one of the things about data races and a lot of bugs in concurrent code is very timing sensitive. So you could run your code 100 million times, like while you're testing before you ship to the customer. Never hit that case. Then the customer that runs the code, but the timing is just slightly different because of the environment they're running the code in, and maybe reproducibly 100% of the time it hits this case, and then the code crashes or does some weird stuff. But more likely it's not that good, because that would be too easy to debug. You just go to the customer site and let them reproduce the problem. What typically will happen is once in every several months it crashes the system, and it's maybe doing something very critical, and the customer gets really upset. And then good luck trying to track it down, because it happens like 1 in 100,000 times or 1 in a million times, but it's frequent enough it's causing real headaches for the customer, because maybe the consequence of that thing going wrong, it causes a really catastrophic failure in the software. So these types of bugs can be like really, really nasty to try to track down, and the compiler can't tell you, because data races is a property of runtime, right? Because in order to have a data race, you have to have a conflicting access happen at the same time. So you can't really tell at compile time that things are going to happen at the same time or not, or at least for the vast majority of cases, it would be something that you couldn't really do by static analysis, like looking at the code at compile time. Even at runtime, it can be kind of tricky. There are tools that you can use to help detect data races. But basically what you want to do is you want to write your code so that you don't have data races in the first place. So try to write your code in a kind of a smart way to at least minimize the chances that these sorts of bugs happen.
Okay, so then this model helps nothing to prevent this situation. It just suggests a way to write a code in a data race tree.
Well, essentially not a suggestion. Well, the suggestion would be the following: if you want to have any clue what your code does, don't have data race, because as soon as you have a data race, you don't know what your code does. Like literally, you have no clue what it will do. And it's not like with some types of things with undefined behavior where it can be kind of more benign. Like we don't really know what it does, but we kind of know what it's likely to do in practice. In these cases, like usually what happens is you really don't know. Like it can manifest itself with very weird sorts of bugs and very weird sorts of failures in your code. So you basically have to be very careful that when you're writing your code that you don't have data races in the code. And the way that we achieve this is there's various different mechanisms we can use for synchronization, what are called synchronization primitives, where we have ways to prevent two threads from doing certain things at the same time. And then by doing this, we can ensure that data races don't happen. But it requires extra things that the programmer has to do, extra synchronization the programmer has to put into their code to make sure that it's not possible that a data race can occur. And a very common mistake when people are first learning concurrent programming is they forget to put some of these synchronization primitives in. And then because of this, they inject data races in their code, and then all kinds of weird things start happening. Any other questions? Yeah?
So by doing that, then aren't we sort of approaching the previous model that of synchronization where you said that was suboptimal?
Okay, well, that's a good question to make, but the difference here is we're not always doing it. We only request the synchronization when we need it. And the basic issue is that for most types of algorithms and things we do, most of the time it doesn't matter. We don't need the synchronization. So the basic idea is with sequential consistency, essentially what you have is that every memory access, whether you need it or not, it's just atomic. Like effectively, that's sort of what the model is saying. What we're saying here is that kind of the opposite. It's like by default, things are not atomic. But because of this, the programmer takes on the responsibility. If they're doing something where a data race could occur, for example, then they take on the responsibility saying, well, this access has to be atomic, or you do some other thing to make sure that there's no data race. And again, like for efficiency, this is kind of what you want to do. Like you want to do the cheap thing normally, and then if you really need the more expensive thing, only when you really need it, then you ask for it. Yeah. Any other questions? So with that said, what I want to start talking about next is threads, how we actually create threads in a C++ program, how we can write a multi-threaded application. So the very first thing we're going to need to do is have some way to create threads. So in the standard library, there's a type called std_thread, or I guess just thread. And basically what it represents is a thread of execution, a single thread of execution for a program. And there's a number of operations that are provided by a thread. They're relatively a small number. There's not too many things that you can do with threads as they're currently defined in the standard. Each thread may or may not be associated with a thread of execution. So a thread can kind of be in one of two states. Like one, it's associated with some code that's running, or two, it's kind of in a zombie state. Like there is no thread of execution associated with it. It's just kind of dead. So we kind of have one of two states that it can be in, which are basically referred to as joinable and unjoinable. So if a thread is actually associated with a thread of execution, it's called joinable. Otherwise, it's referred to as unjoinable. So you effectively have two states that a thread can be in. The default constructor, if you default construct a thread, what it will do is it will create an unjoinable thread. It creates a thread that's not actually associated with any thread of execution. There's not any executing code associated with it. It's kind of like a placeholder that you could later use and fill in with something that would correspond to a thread of execution that's running. But it's not actually associated with any thread of execution. We can also construct a thread with a constructor where we provide some kind of callable entity. So what I mean by callable entity is either a function or functor, like something that you can apply the function call operator to. And basically that means you could either give it like a function or you can give it a functor, which is an object that overloads the function call operator. And then you can also provide arguments that you might want to pass into that function or functor as arguments. And this will create a new thread that's actually executing the function that you specify, passing in the particular arguments that you provide. The arguments that you provide for a thread, they're always copied. They're propagated by copying. So if you want to actually pass things by reference, there's something called reference wrapper in the standard library. What it is, it's just a type that wraps another type, but makes it behave as if it's behaving like a reference. So this is what you would need to use if you wanted to pass some parameters to a thread function by reference. A little bit more about the thread class. The thread class is movable but not copyable. You can't copy threads. Essentially, it would be like, what would the meaning of copying threads be? It's not really clear, so it doesn't provide any sort of copying operation, but you can move them though. Each thread has an ID, which is unique. Every joinable thread has a unique thread ID to distinguish between the different threads that are executing different code potentially. And there's also a sort of a special value for the thread ID, which is just a thread that's not joinable, like one that doesn't represent any thread of execution that's running. So you can distinguish between these types of things based on thread IDs. And I think that's all I want to say for this slide. Any questions? A little bit more about the thread class. So it provides a number of operations, not too many. One of them is a join operation. So what a join operation does, you can apply the join operation to a thread. It waits for the code that's being executed by that thread to complete, and then the thread becomes marked unjoinable at that point, and then the join operation would return. So it basically gives you a way to wait until the thread is effectively done whatever computation it's doing. There's also what's called a detach operation. What this does is it just dissociates the thread from the thread object. The actual thread that's running sort of gets separated from your thread object, and it just goes off and runs independently from the thread object. So this is what detach means. If you move from a thread, the object that you move from becomes a thread that's unjoinable. In other words, when you propagate a thread from one, like a thread object or thread value from one thread object to another thread object, the one that you move from just becomes like a zombie object. Like it's not associated with any thread of execution. Whereas the thing that was actually running will then be in the moved to object. Another thing to watch out for when you're using the thread class is that it's considered to be a fatal error if you hit the destructor of a thread and the thread is joinable. In other words, if you haven't actually called the join operation to wait for the thread to complete what it's doing, and this will also mark the thread unjoinable before it returns. If the thread is actually still joinable at the point where the destructor is called, an exception will be thrown. This is required by the C++ language specification for the standard library. And this is a common sort of mistake to make. This is why I point this out, is that maybe you forget to do a join operation maybe because for some reason you didn't really need to do the join, or at least you thought you didn't need to do the join. Then you hit the destructor, and then you get some kind of error message like uncaught exception, and basically the cause was that the thread never got waited on. A few other things with respect to the thread class. There's a static member function called hardware concurrency, and this basically returns the number of hardware threads that can be run simultaneously, because sometimes you might want to make the number of threads that your application uses depend on the hardware. So maybe you have an 8-core processor, maybe you want to fire up 8 threads, like 1 for each core, assuming that maybe there's nothing else running, or most of the time there's nothing else running, so you want to kind of fully utilize the cores that are available. This function, however, is allowed to return 0, just meaning, well, there's not really a well-defined meaning to the number of hardware threads that can be run simultaneously, just depending on the particular hardware. Some hardware, it may not be clear what this value should return. And then maybe the last thing to say with respect to thread creation and also joining of threads, these establish what are called synchronizes with relationships, which I'm going to talk about more a little bit later. And this is kind of coming back to one of the questions that was related to, like, how do you avoid data races and so on. There's certain types of operations that introduce what are various different types of synchronization relationships, so that you can say something happens before something else in the code. Therefore, all of the side effects of that first thing that happened earlier, that happened before something else, must be visible to that thing that occurs later, happens after. And one of the relationships that are created by the thread class is when you create a thread or you join a thread, this establishes what are called synchronizes with relationships, which I'll talk about in more detail, which essentially say that something happens before another thing. And then if you can say something happens before, for example, how this can help you with respect to preventing data races and so on, if something happens before another thing, they can't happen at the same time. Then therefore you can eliminate the possibility, for example, that there might be a data race that's caused by this, because this would require both of them accessing the particular piece of memory at the same time. So we'll look at this a bit later. And I think I'll stop here for today, because we only have maybe a minute left, and I probably can't talk about much more in the time that's left. Any last questions?